The cosmos has always enticed humanity, with its enigmas. Then on a clear and quiet evening, the James Webb Space Telescope cut through the darkness of space and uncovered a revelation that may reshape everything we know. Scientists glued to their displays watched in disbelief as fresh data emerged, revealing something astonishing. Lights eerily reminiscent of those from our own urban landscapes, flickering on a remote exoplanet in the constellation Leo. This world orbiting a star 120 light years from Earth presented unmistakable evidence. Glimmers of light scattered across its twilight region, uncannily similar to cities glowing beneath Earth's night sky. Is this humanity's first glimpse of an advanced alien society? Let's unravel how Webb detected these mysterious city-like lights on the exoplanet K2-18B, 120 light-years away. A global team recently identified the presence of carbon dioxide and methane in K2-18B's atmosphere. Thanks to the cutting-edge technology on board the James Webb Space Telescope, unlike anything in our solar neighborhood, this world is both smaller than Neptune and significantly more massive than Earth. While most exoplanets we've studied have been either turbulent, scorching, or utterly inhospitable, K2-18B captured astronomers' attention due to its Earth-like potential. Its sheer size, roughly 2 to 3 times Earth's diameter and nearly 9 times its mass, makes it a fascinating candidate in the hunt for alien life. Orbiting within the habitable zone of its star, it has just the right conditions to support liquid water, a crucial ingredient for life as we know it. Scientists suspect it's a Hyson planet, a type of world blanketed in liquid water beneath a thick, hydrogen-dominated atmosphere. Unlike Earth, where nitrogen dominates our skies, K2-18B's atmosphere appears rich in hydrogen. Interestingly, the sunlight it receives is comparable to that bathing Earth, and temperatures on the planet, disregarding atmospheric effects, seem strikingly similar to ours. Characterizing atmospheres on planets like K2-18B is challenging but within reach, even with data from Hubble, ground observatories, and now the infrared Webb telescope parked a million miles from Earth. We still can't definitively say if such planets are truly livable. The detection of a significant amount of carbon dioxide and methane and a surprising lack of ammonia supports the idea of a potentially oceanic planet beneath a hydrogen-rich sky. Adding to the excitement, scientists picked up a signal that might indicate the presence of dimethyl sulfide or DMS, a molecule on Earth produced only by marine phytoplankton. However, researchers urge restraint. While the possibility is thrilling, confirming DMS's presence will require further evidence. On our planet, DMS is tightly linked to biological processes, but it's too soon to make bold claims about life. Carbon, just a single atom, is the foundation of every living organism on Earth. It shapes ecosystems, governs our climate through its role in greenhouse gases, and underpins modern technology. It's only natural that scientists would use carbon-related molecules as clues in the search for extraterrestrial life. When astronomers discuss a planet's habitability, they often refer to the habitable zone, the region around a star where conditions might allow liquid water to exist. This idea, though basic, gives us a starting point to estimate where life could arise. Of course, experts in astrobiology will argue that this definition is oversimplified, and they're right. But as we look further from Earth and our data grows thinner, we have no choice but to simplify our models. Today's powerful telescopes do more than just sharpen these models. They enable us to make direct observations. A planet's climate is shaped by a network of forces. The energy it receives from its star, how much it reflects, and the composition of its atmosphere. ALBO, the measure of how much solar radiation a planet reflects, is affected by factors like clouds, ice, vegetation, and even aerosols suspended in the atmosphere. All of these can change over time, which is why predicting climate is so complex. The sunlight a planet doesn't reflect is absorbed by its surface and later remitted as infrared energy. That's where greenhouse gases step in, trapping this heat and warming the atmosphere. These gases are essential, but only in the right amounts. Too few and a planet freezes. Too many and it becomes a pressure cooker. Take Venus for example. Once potentially Earth-like, it spiraled into a runaway greenhouse effect. For over a billion years, Earth's climate has remained relatively stable thanks to natural carbon dioxide regulation. But human activity, specifically fossil fuel use, is now disrupting that balance. In exoplanet research, scientists are cautious about labeling a planet habitable without understanding its atmosphere. That's why identifying gases like water, vapor, methane, carbon dioxide, and ozone is central to all exoplanet missions. To measure a star's energy output across the spectrum, including the ultraviolet range, we depend on tools like the Hubble Space Telescope. If Hubble fails, we lose our only current way to gather this critical data. While we haven't yet confirmed life on another world, the James Webb Space Telescope could be the first to reveal signs of life in an alien atmosphere. If DMS is truly present in K2-18B's skies and in amounts 20 times greater than Earth, it might suggest something is alive there. But Dr. Niku Mandasudan of the University of Cambridge, who led the research team, warns against drawing conclusions too soon. Confirming DMS will take more data, and the original detection was too faint to be conclusive. That's why other scientists stepped in, analyzing whether the signal might have been confused with methane. Their simulations suggest that separating DMS from methane is beyond Webb's current abilities, at least with the instruments used so far. To improve their chances, astronomers are turning to the telescope's MIRI mid-infrared instrument to probe deeper into K2-18B's environment. They're exploring whether DMS might be a better biosignature for hydrogen-rich worlds than oxygen, which is so prominent on Earth. Is this setback disappointing? Not at all. If anything, it reaffirms the importance of studying planets like K2-18B as we refine our understanding of habitability in unfamiliar environments. As Dr. Tai puts it, why do we keep looking for life in space? It's like being in the desert at night, hearing a sound. You shine a flashlight to see what's out there. That's what we're doing, too. Meanwhile, Webb has uncovered something even more ancient. A chain of extremely old galaxies, possibly the earliest known strand in the universe's cosmic web. Those stars appear evenly scattered across the night sky. They're actually woven into a vast structure connecting galaxies like beads on a filament, with unimaginable emptiness between them. And now, scientists have traced this structure back to the dawn of time. Data from Webb revealed a string of 10 compact galaxies stretching 3 million light-year, a filament anchored by a brilliant quasar and born just 830 million years after the Big Bang. Dr. Shia Fan of the University of Arizona marveled at the discovery. I expected something, but not this long, thin, well-defined structure. The team is part of the Aspire project, which investigates how early supermassive black holes helped shape galaxies. It's thought that these black holes, through their gravitational pull and energetic outbursts, helped sculpt the cosmic web we observe today. Over time, this filament may collapse into a massive galaxy cluster like the Coma cluster, relatively close to us at 330 million light-year. Webb also continues the legacy of the retired Spitzer telescope, especially with its exploration of the TRAPPIST-1 system. This nearby star system, about 40.7 light-years from Earth, harbors 7 Earth-sized planets. One of them, TRAPPIST-1b, has already yielded groundbreaking results. It's the first time we've captured light emitted by a planet outside our solar system. This is a pivotal step in assessing whether such planets can support life. Although TRAPPIST-1b is Earth-sized and rocky, its lack of an atmosphere and surface temperatures reaching 450 degrees Fahrenheit make it unlikely to support life. Still, it's encouraging. Stars like TRAPPIST-1 are more common than Sun-like stars and more likely to host rocky planets. The downside? They're often violent, unleashing radiation that can obliterate atmospheres. But thanks to Webb's infrared vision, we can continue studying these alien worlds and perhaps one day find a planet that mirrors Earth in more ways than just size. And who knows, in some distant future, should catastrophe strike our home, perhaps one of these worlds could offer humanity a second chance. NASA cracks the code behind a giant, puffy marshmallow planet. After years of speculation, NASA has finally unraveled the mystery behind a bizarre, oversized, and incredibly light exoplanet, affectionately dubbed the Marshmallow Planet. Thanks to the powerful James Webb Space Telescope, scientists now have a clearer understanding of how WASP-107b, a planet located roughly 200 light-years away, grew to an enormous size while retaining such an unexpectedly low mass. The gas giant was initially discovered in 2017 through observations made by the Hubble Space Telescope. Although the planet is around 75% the size of Jupiter, it contains less than a tenth of its mass. Imagine a massive balloon drifting through space. That's essentially what WSP-107b is. While most gas giants are easier to categorize due to their heat and size, this puffy planet has puzzled astronomers for the past 7 years. Using its mass, age, radius, and estimated internal temperature, researchers initially theorized that the planet possessed a thick outer layer made up of hydrogen and helium surrounding a relatively small rocky core. But the main question remained, how could a planet with such a tiny core gather so much gas without expanding into something more like Jupiter? Dr. David Singh of Johns Hopkins University, lead researcher on a separate study published in Nature, explained, WASP-107b stands out because it's cooler and has a mass closer to Neptune, unlike the hot Jupiters we typically examine. That difference gives us the opportunity to detect molecules like methane, which reveal the planet's chemistry and interior structure, insights we can't always gain from hotter, more massive planets. Due to its size and orbit, WASP-107b is perfect for a method called transmission spectroscopy. This technique analyzes how starlight filters through a planet's atmosphere to identify the gases it contains. By leveraging the high-resolution data from the James Webb Telescope, scientists have now identified several atmospheric compounds: methane, water vapor, carbon dioxide, carbon monoxide, sulfur dioxide, and ammonia, among others.